the Fermi distribution times the density of states. Okay, this is in terms of energy. We always do this kind of calculation a lot in semiconductor physics. Fermi distribution is expressed in terms of energy. And this gives you, you might have a something like this. Okay, you might want to find out how many free electrons I have. You will integrate from the bottom of the conduction band to the Fermi level. Okay, this would be a Fermi level, right? You just do this integral to calculate the number of electrons you have. So if you know the density of states, this kind of calculations become simpler. It's not like microwave. Microwave, you always want to think in terms of k vector, right? So this is different. So are there any other questions regarding this? Yes?
What's the meaning of G again?
G is the density of states. It's the number of modes or number of states you have in the case of the first derivation per unit wave number. Okay, in 1D, 2D, and 3D. This will be per unit area of the wave number. This will be per unit volume of the wave number. And then we want to convert those to per unit energy in 1D. Actually, energy is just one value. Okay, energy does not have 1D, 2D, or 3D. So you need to map some of this thing from 1D, 2D, and 3D to 1D, because energy is always measured in terms of just a scalar number. Okay? So what happens then is that, for instance, if I were to do this in 1D, okay, 1D I might have an EK diagram that looks something like that. Okay, EK diagram that looks something like that. You can see that if I have modes in the periodic boundary condition case, the modes are counted with uniform spacing in the k direction. Right? It was a 1D thing, right? They counted. Then you see that when you count them in the E direction, they're actually not evenly spaced anymore. So the density of states in the E dimension is different from the density of states in the k direction. Okay? You see that this mapping is not linear, it's a parabola. This is what this the E dk does, or the KDE does, is give you the slope of the mapping. Okay? But eventually we want to make L1 go to infinity, L2 go to infinity, L3 go to infinity. And when that happens, then delta k just becomes dk. Delta k x becomes dkx. Delta ky becomes dky. Delta kz becomes dkz. This is like Fourier series becoming Fourier transform kind of thing. So actually the values of L all disappear in the final count. We start with finite L1, finite L2, finite L3, but we let those be infinity so that we can replace kind of approximate calculus with exact calculus. And then these numbers are exact in the sense that decay is going to 0. Okay? So we let these numbers be infinity so that this spacing becomes very, very small. Okay. Are there any questions? Any other questions? That's a good question. Okay, let's look at the density of states of a quantum walk. So let's look at this. So in that case, then V is a function of Z only, and the effective mass is a function of Z only. We go and make this material by MBE machine, and then we get the effective mass to be changing in only one dimension. We can also get the potential to change in only one dimension. Then the effective mass Schrodinger will look something like this. We have to sandwich the effective mass between the gradient operator and then we can look for the eigenmodes of the system. We change this partial t, which I've erased over here, to just a bar omega, and then we change that to E. And how do we solve this problem? We solve this problem by separations of variables. Okay, because in the z dimension you have layers that are changing only in the z direction, but the electron is free to move in the x and y direction. So we're going to do this to write the gradient operator into a transverse operator plus the z variation, where the transverse operator is x partial x plus y partial y. Okay. I'm going back to my old habit of writing this in terms of x hat and y hat again. Well, I guess you know what I mean. I should write A1 hat and A2 hat if I want to follow the notation that I use. So if you do this, then when you substitute into the above, then only the z variable matters with this, and you get two equations. You get an equation that looks something like this: h squared over 2. The transverse part of the operator would never operate on the effective mass. Okay, so we can take the effective mass out of the transverse operator. So the first part of this thing will look like this, but then there's a partial z variation that gets left behind, and that has to be written like this. So the Laplacian operator gets broken into two terms. One term involving the partial z operator, where you cannot commute the effective mass with the partial z. And the other one is partial x and partial y operator. You can commute the two and take the effective mass out. And then of course you're left with the last term. Okay. Do you want me to show this in somewhat more detail, or you can agree going from here to here? I don't need to show you the details, right? Can you accept it? That if you substitute this into the above, I get two terms. The partial z term will have the NE still sandwiched in between the derivative operators. So if we do a separation of variables, then we write this as being a z function times a transverse function where r sub s, okay, is x hat x plus y hat y, transverse variable. And if we substitute that back in to this thing, we get two equations. Okay, this thing will not operate on this part, and this thing will never operate on this part. So you can commute the two and take some of these things out. You will have an equation that, I guess if I go into the detail, it will be something like this. Phi nz Laplacian squared phi s rs. This is what happens to the first term. You can take this phi nz outside. The second term, you can take the phi s outside, and then you have the phi nz inside that you have to leave behind. And then you will have Vz phi nz phi s rs plus E phi nz phi s rs Okay, so this is by the separation of variables. And of course, the trick there is usually to divide this whole equation by phi mz and phi sc. That's one way. And then look for the two equations that you need to satisfy. You divide this equation by phi m phi s. And then you get functions as functions of z only, and then you get one that's a function of r sub s only, and then you equate the two functions separately, and then you get two equations. Okay? So let me not go through the details, but just tell you what the two final equations are. So the first equation for the size of SRS would look something like this. And let me give it a new eigenvalue that's different from E. Okay. And then the second equation that I have will look something like this. Partial z 1 over me partial z size of nz plus b of z size of nz, and then I will give you a different eigenvalue, e sub n size of nz. You can reconstruct the above equation by just solving these two equations, but the eigenvalues are different. One is dn, one is es. So finally you have to set E equal to es plus en. Okay? To get the two to satisfy each other. Actually, I can show it to you quite rapidly if I just substitute this back into this equation. If I just substitute that back into that equation, I can derive the second and the third equation quite easily. So if I assume that the transverse variation, the wave function in the transverse direction satisfies this equation, I plug it back in, I will get h squared over 2 me psi mz. And then because of this equation, this thing can be replaced by, let me see, instead of writing all this bunch over here, I can replace this times this with just es psi s rs. Okay, the first part becomes just this. And then the second part is just h squared over 2 psi s rs 1 over me partial g psi n. The second part. The third part remains the same, bz psi nz psi s rs. And then the right hand side remains the same. Now if I take this to the right hand side, okay, I get the last equation. Okay, if I define E to be, if I define En to be E minus Es, I take this E to the right hand side, lump it together, I get the last equation. I get this equation. Okay? I just cancel. I will cancel this away because they're useless. Okay, so I will get the last equation for that reason. Is that fair enough? Okay, you're convinced that they are separable. And then we need to solve this equation separately then. We need to solve first this equation separately, and then after that solve the other equation. So in order to solve this equation, it's rather simple. We let Rs be something of this form. A transverse wave function. Rs is only a function of x, y and so on. So this is a wave that is propagating in the x and y direction. You have a lot of layered medium in the z direction, but there will be a mode that propagates in the x and y direction. This might be y, this might be x. And this is the transverse wave function. And then you can plug that into this equation, you will get ES must be equal to h squared ks squared over 2me. Okay, let's assume that me is a constant. If it's not a constant of z, then you have trouble at this stage. Okay? Let's assume that it's a constant to make life simpler. There are other ways of treating the problem with me is not a constant of z, but let's make things simpler at this point. Then you need to solve the second problem. Okay? You need to solve the second problem where En is E minus Es, which you have already found. And then you can solve the second problem as an eigenvalue problem. It may not have closed form. It may not have closed form because V of z can be complicated. You can make me a constant to make life simple, but it would not still have a closed form if V of z is complicated. Unless it is a very simple potential wall. It is a very simple potential wall, like a square potential wall. Then it's like a dielectric waveguide problem. Okay, or infinite potential wall. If this goes to infinity, then it has a closed form. But for other structures that looks like that, it may not have a closed form. Okay, and you might have closed form numerical method if you have a complicated structure like that. So it depends on how the 1D potential looks like. It has a closed form, it has no closed form. Okay. So if you solve this 1D problem, say if we solve this for the infinite potential wall problem, we get confinement of the energy in the z direction, or confinement of the mode in the z direction. Then we might have modes that look like this. And I have maybe E0, E1, E2 kind of thing. Let me see what I use. I use E1, E2, and E3. E1, E2, and E3 in the lecture. So the z direction gave me different eigenmodes. Okay? And then there's no confinement of modes in the x and y direction, and I don't have confinement in the x and y direction, so these electrons are free to roam in the x and y direction. So I have a continuum of modes in a sense. So I can think of this as a 2D problem where I need to count this mode. If I need to count this mode, I need to count the density of states as well. So actually I can find in the 2D direction what the density of states is in the E sub s variable. In this, I think of this as just a 2D problem. I need to find this density of states. Okay, then it will be given by the density of states in the 2D problem in the k space times 2 pi ks. Okay. Okay, we know how to find this 2D density of states for a 2D problem previously. This is entirely a 2D problem. And we did an example for the 3D problem. Okay, this turns out to be 2D. This thing turns out to be 1 over 2 pi squared if we count in the k space. Okay? And then we have to look at this density of states in the k space. It will be kx, ky. If we use periodic boundary conditions, you get all these modes that we find. Okay, we've used periodic boundary conditions to solve this problem first. We get a thing, and then we get all these modes. And then we have to count the modes for a constant E. If this E sub s is a constant, you find that k sub s squared is a constant. So we are actually looking for the number of states we have in an annulus region. Okay, that annulus is given by 2 pi ks times dks. Okay. This annulus is given by that. And then we have to multiply by a factor of 2 to take into account that every state can emit 2 electrons, spin up and spin down. And then we need to divide this by dE, multiply by dE to get this to be G to the dx. Okay? So we can figure out what the EDS is. This should be ES should be from this equation. Okay? So if you plug that in, then you get the KS, or you get the ES. The KS is equal to H squared KS over M sub E. And you plug this in, and then if you plug in everything correctly, you have a K squared over there. And then I have this as my final answer. Okay, this Ks cancels with that Ks. This is a constant. And there's no more Ks dependence. So finally, 2D E sub s is equal to ME over pi h squared. Okay, there's no more Ks dependence in this. Okay, this Ks cancels that Ks. And you know why I multiply by 2 pi Ks? Because this is the circumference of this circle, and the Ks is the getting the area of the annulus region. Okay. So the density of states turns out to be a constant for the energy space, energy variable. Okay. So what happens is this. That if you just look at the one of the bands, say if you just look at one of the bands where En is the lowest mode, then you have this. This is my E, okay? This is my E1. E versus Ks. E versus Ks will be something like E is equal to H squared Ks squared over 2ME plus E sub n. And if I were to plot this for different E sub n, and if I take E1 to be the first value over here, then the first band will look something like this. If you pick E1 to be the first eigenmode, for instance, then the first band will look something like this. And then if I pick En to be E2, then I will get another band. This is E2. This is E3. So I get what is known as subbands for the EK diagram. Okay? So for different EK, I have a different EKS relationship. For different E sub n, I have a different EKS relationship. And those EKS relationships will look something like this. I know the density of states in the Ks space, this should be Ks space, is a constant. It was a constant. Okay? And it was a constant. But then I have to change that density of states to the E space. I will have to do this mapping. Okay, when I do that mapping, I have this thing that is the Ks, the Es is proportional to 1 over Ks. Okay, so it seems that the smaller Ks is, the larger this number is. Okay, you can see the mapping, it actually maps things into a denser and denser space. Okay, that's why it goes as one of this. But then I also have to multiply by 2 pi Ks. 2 pi Ks exactly cancels this effect. 2 pi Ks means that I have to multiply by the circle that goes around in this direction. Okay, there was this. Ks, I have to count all the states in this circle. And the number of states I have in that circle is proportional to Ks. Finally, it becomes a constant. So I have no density of states, but when I reach here, I get a constant density of states that's independent of Ks, is what it means. Okay? Is what it means. Because the compression due to this factor cancels the expansion due to this factor. Okay? So the density of states looks like that. But if I were to merge, and count my density of states in the E space, okay, this is my density of states. For this problem over here, I will find that I don't get any density of states, no states before I reach E1. When I reach E1, I suddenly jump to a constant. Okay, jump to a constant value. And that is this constant. That constant over there. Where was my constant? Yeah, this constant. Okay. And then after that, it will remain constant until I pick up this other subband. If I pick up this other subband, I pick up new density of states again. Okay. So it will jump again to E at E2. Okay. But it jumps by the same constant. So this constant is the same. This jump is the same as this jump. And then I march until I see E3. And then I jump by the same amount as well. So it seems that the density of states will look something like this for the quantum walk. This is the subband effect. I pick up first subband, I get a constant value. As I march along, I get the second subband. Density of states contribution from the second subband. As I march along, I get the density of states contribution from the third subband. So it actually looks something like this, but I haven't drawn it very well. Okay, maybe this should be further out. And it turns out that this curve here should follow this curve that I drew over there. I erased it. Should be that of the bulk material. Okay. So what happens is that as you make this quantum wall in the transverse direction larger, if you make this dimension larger, okay, this width of the quantum wall larger and larger, you get more and more modes, right? What happens if you make the quantum wall larger and larger? You get more and more modes. So what happens then is that the subbands that you get, okay, also become more and more numerous. So what happens is that if I were to draw this picture for the case of a larger quantum wall, then you have subbands very close to each other. Okay. Instead of spacing far apart, these subbands will be very close to each other. So if you march now and look at the density of states as a function of E, this diagram would change. It will actually look something like this. Okay. It will jump very quickly because you have a lot more subbands now. Okay. It actually follows the curve, the density of states of a bulk material. That is reasonable because as you make this quantum wall larger and larger, then the quantum wall looks like a bulk material. And this is the curve of the bulk material, and all these step functions actually follows the density of states of the bulk material. Okay? Otherwise, it looks something like that. You do see the kind of effect in electronic transport when you do calculation, step function-like behavior. So are there any questions so far for that of the quantum world? And then let's go to quantum wire. Much time left. Quantum wires, then what you have is that you have confinement in 2D. Okay, you have a wire. You see the confinement in one dimension, which is what we did here, confinement in one dimension. You have the electron confined in 2 dimensions. Okay, so the equation will look something like this, that this is being confined in 2D, this equation. And then in the z direction, there's no confinement. The potential is also a function of x and y. And z direction has no confinement. So this thing is free. The electron is free to roam in the z direction, but it's confined in the x and y direction due to either the effective mass change or the potential change. And then E of psi. And then again, you solve this by the separation of the variables. You assume that the electron is free to roam in the z direction, but confined into modes in the x and the y direction. You substitute that into the above equation. Then you get an equation for the transverse modes. Okay, by the method of separation of variables. This would be a function of x and y, for instance. Psi of Rs plus V of Rs psi, this should be Mn of Rs plus Emn of psi Rs. So you're now solving a confinement in the x and y direction. It could be like if it's a rectangular waveguide, then you can find closed form solution for this. If it's a circular waveguide, you can still find closed form solution for this. If it's arbitrary shape, then you might not have a closed form solution. Then you have the other one, the other solution, which is that if this satisfies that, then you have the other equation. Psi of R, the z variation. Okay, z variation is very simple. It's just equal to that. Okay, and then it's equal to E minus E Mn e to the ikz. And then you can figure out what this should be, and you figure out that E has to be something of this form. E Mn must equal to E minus h squared over kz squared over 2Mn. Okay? So then you figure out the density of states for this thing. It looks a little bit strange for a quantum wire. Then you find that kz is equal to square root of 2me over h bar square root of e minus Emn. Okay. For rectangular waveguide, you can find this transverse mode quite easily. It's something that you learn how to do in ECE 350, for instance, n pi over L2 squared, and something like this. Okay, you can find this quite easily for Emn. And then you can actually find your 1D density of states in the E space by doing this mapping. dkz over dE dE. Okay, then you can figure out that this has to be the density of states in 1D. Okay, then why the factor of 4? The factor of 4 comes about because it's a factor of 2 coming from the electron spin, and a factor of 2 coming from the fact that in 1D, if you plot the EKZ diagram, okay, you have one mode coming from here plus another mode coming from there. Okay, there's a plus Kz mode, there's always a minus Kz mode. Whereas in this one is multiplied by 2 pi Ks. Okay, you have to count all the modes in this annulus. But in 1D you count the modes in these two extreme ends. Okay, you multiply by a factor of 2 to get a factor of 4. And then if you work this out properly, then you get the Kz dE or dE dKz. You can figure out that very easily. Must be equal to h squared Kz over ME, right? This equation, you can figure that out. And then the Kz dE, you can figure that out. The Kz dE is proportional to 1 over Kz. Okay? And then 1 over Kz is proportional to 1 over E minus ENN. Okay? The distinguishing feature is that this thing is a constant in one dimension. We figure out what G1D is. G1D was, we did the 1D case previously. G1D Kz was given to be just 1 over 2 pi, right? Just 1 over 2 pi. Remember we did this density of states in the case space, it was just given to be that. So if you plug this in, this distinguishing feature is that this thing has a singularity. Okay, this thing has a singularity. So G1dE is equal to 1 over pi 2ME